Okay, so whenever you say we start. So start.
Yes.
Okay. Dear all, welcome to Quantum and Classical Statistical Physics Seminar. This week, our speaker is Dr. Denis Boyer. He did his PhD from University Thierry at Marie Curie in 1995 with Pascal Biot. Then he did his first postdoc in University of Chile, and then second postdoc in Florida State University. After that, he started working in UNAM from 2002. He is quite well known for working in stochastic processes, animal movement, population dynamics, network, and all other classical stochastic processes you can think of. So today his talk is anomalous diffusion of random walks with memory.
Okay, thank you, Soham, for the presentation and for the invitation. Thank you to be here. For me, well, it's my first time giving a talk in Guadalajara, and my second time in Guadalajara. I'm very happy to be here this week. And so the initial motivation for studying these problems starts with the study of human mobility and animal mobility. So human mobility is a relatively recent subject of research. So I put the example of two, one of the first papers on the topics of the year 2006 or 2010, where people measured and studied how people travel from one city to the other in the United States, or how a person within his city lives, where he lives, go from one place to the other, for instance, from home to work or from work to home, and which place are visited. And it is at that time it was quite not so easy to find where people move and when, because smartphones did not exist, or were kind of at the beginning, and GPS were not so common as now. And so the important word here is to the study of individual trajectories and not population flux or demographic dynamics, but really to know from particular single individual how do they move, and to study their statistical property if there are anything interesting to say about it. And something very related topic is in ecology, thanks to the technological advances. It is also possible to track this now with a very high precision, the movement of animals in the wild. And so the reasons for studying that are very different, although the kind of tools and methods are very similar than what we can use here. So movement is essentially very important for life, because animals need to find food to reproduce or to escape from predator, and for this activity they need to go from one place to the other. And this brings us to models, how we can model these kinds of phenomenon. And so this is quite applied at the beginning, because of course, depending on this pattern, they can have some important implication on traffic problems, or the spread of disease, on epidemics. But on the theoretical point of view, also the model that we can, that are, let's say, that we can make from the analysis of the data, can have their own mathematical and theoretical interest, right? So, so we as physicists, we are used to track and to analyze single trajectories. Basically, since the pioneer work of Jean Perrin on Brownian motion, So that was this microscopic observation of diffusing Brownian particles. And actually, in movement ecology, which is a branch of ecology which is really focused on the movement of individuals, of living organisms, one of the basic models, actually, for decades has been the simple random walk. So very simple model for describing the movement not of particles but of animals. And we also rely a lot on this guy that I guess you know or have heard of, which is Andrei Markov and the Markov hypothesis. So let's assume that we have a stochastic process, for instance, the successive position of a diffusing particle or a diffusing or moving individual, starting from a position x naught up to a time t minus 1, where t is an integer. So we have a regularly measured positions. So if we know the whole trajectory, we are able in principle to make a prediction on what will be the next position at time t. Right? But we do not know, but we like to calculate the probability to find the particle near a given position. And the Markov hypothesis assumes that that whole object depends only on the last position available at time t minus t minus 1. And so there is no memory in the process. And the simple example, maybe one of the simplest, is a simple random walk, where you have a particle diffusing on a 1D lattice, for instance, starting at the origin, and we can introduce the occupation probability. So what is the probability to find the walker at position 10 and at exactly t step? So at each step you can take a right or a left step with equal probability 1/2. So everything depends on the previous step because these steps are completely independent. You just draw coins. So you can write things like master equation. So the probability that we are looking at depends on the probability to find the particle at time t minus 1 only. So it's a local in time. So here it just tells that to be at site n at time t, you were either on the neighboring site n minus 1 at time t minus 1, and you did a right step, or you were on the site to the right and you did a left step, so which occur with probability 1/2. This can be solved analytically. In the large time or n limit, this boils down to the simple diffusion equation that we can solve, and we know that the solution are given by simple Gaussian distribution. So for a particle starting at n equals 0, at time t equals to 0. So even the parity of the Gaussian distribution, there is no net displacement. So there is the same probability to find the particle at the left or at the right of the starting position at all time. But there is a mean square displacement. So this, the first non-trivial quantity to analyze here is basically the square of the position, which is average over all trajectories. And this grows linearly as the number of steps. So that's a famous Smoluchowski-Einstein law for diffusion. This is called normal diffusion because this is a Brownian motion and many other examples in physics. And so since it is a slide of the picture, I also put the picture of Denis Boyer, which was maybe the first mathematician to study this type of simple model in the 30s. And actually found many non-trivial properties of simple random walks on lattice. And at the end of the talk, if I have time, if I will come back a little bit into this. So the connection is not very obvious because the topic of my talk actually is to deal with path-dependent processes. So, which are strongly non-Markov processes and for which we know very little. So we cannot write this type of equation that I just showed for the occupation probability in general. And there are some examples, for instance, known from the mathematics literature, which for instance, the reinforced random walk. So the idea is that the probability to cross the edge, for instance, will depend on the previous number of times that you use that edge. So, for instance, the probability to make this move will be proportional to the number of times you already did this move in the past. So the probability, the transition probability are not constant, and they depend on the whole history of the work. Right? So this is motivated by ant foraging or bacterial movement, so which are organisms that leave pheromone or chemical signals. And if we assume that these toward which they are themselves attracted. So these are processes which are self-attracting. And so if you assume that these signals do not evaporate, so the worker tends to to use some part of its trajectory very often. And more often they are reinforced because the higher, so the more likely to move across this edge will increase, of course, the number W by 1. And so it will also increase the probability to cross it the next time, etc. So there is a kind of reinforcement. And the exact results are very rare. They are limited to finite graph or on the infinite time limit. And there is actually a connection in the very long time limit with Markov process, simple Markov random walk, but in a disordered environment. And I will not go too much into detail for this. And there is another, in another spirit, a little bit different. We have the same kind of processes, which are called vertex reinforced process. So, which loosely speaking is like saying that we want to revisit familiar places. For instance, here the probability to go to a nearest neighbor site will be proportional to the number of visits, or will be a function of the number of visits of that site received by that site in the past. So, for instance, the transition probability will be proportional to an increasing function of the number of visits. So the more you visit a place, the more you want to come back to that place. And this is actually very relevant for human mobility and also for animal mobility. So there are many studies that have shown actually that people tend to come back to places where they have been there often, and that probability increases with the popularity of that of a particular site. So it depends. So it's a little bit the intuitive idea that if you like a place and you want to revisit it again, and you will like it more, and you will just kind of take on the side the other possibilities. I mean, if you want to go to the restaurant, for instance, like we did today, or yesterday, you go to familiar place again and again, and you don't really visit necessarily other places which are nearby, right? So these problems are even less well understood mathematically than the previous one. So quantity like occupation probability, mean square displacement are basically unknown. And in general, would like to quantify how this self-attraction, this non-Markovianity, affects on basic quantities. And does it lead to anomalous diffusion? So what we call by anomalous diffusion is basically anything which is not like Brownian diffusion, like the small short scale strain law, or and the other property linked to it. Do we have other phenomena that can arise, like localization? So the work does not diffuse anymore, so it becomes very limited in a restricted region of space. And other property like recurrence transpassage. And what would be the biological advantage? I mean, for an animal, why would it be important to have this kind of algorithm right in the brain? So here, from a theoretical point of view, and a little bit also empirical, I want to present a class of exactly solvable models with this linearly reinforcement property. And so I would like to start with the first example. So we have a random walker on a line, and they are basically a mixture of two movement modes. So there is a parameter q, and with probability 1 minus q, we do a random step with probability 1/2 on the each side, and with probability q, the complementary probability, you reset to a previously visited site. So here we have, for instance, a set of visited sites since t equals to 0, and the worker decides to revisit site j. And the probability to visit j among all the sites that have been visited is proportional to the number of visits that this site has received. So there is a preferential. So it's a non-Markov extension of a class of process which are quite well studied and well known now, which are the diffusion and the resetting or resetting processes, which has been introduced some time ago by Evans and Majumdar. So I just briefly want to recall what these processes are about. So let's assume that you have space and time, you have a random walk that evolves in time, and then so you reset exactly like in the previous slide, but you reset to the single point, to the starting position. That's it. And then you have a probability q or the rate r to reset to be x. And so that's basically a generalization. So this can be described by this generalization of the diffusion equation. So it is a class of relatively simple non-Markov process because you have to remember your current position and the initial position, and that's it. Right? So you reset to the initial position from time to time. And so an interesting property is that this system forms some non-equilibrium steady states. So this, if I put the time derivative equal to 0, this equation has a non-trivial solution, which is given by exponential, which is time independent here. And so we don't have a Gaussian anymore, but we have exponential at very large time. So the walker becomes localized near the starting position. It's right like this double exponential, sometimes it's called the Laplace distribution. So if we come back to our model with linear reinforcement, so starting from the origin, we do this completely random walk, and then at some point there is a resetting event. So instead of going back to the origin, we reset to a previously visited site. And we choose a visited site. For instance, the probability to revisit a particular site n would be proportional to the number of visits, 5 here, for instance, divided by the total number of positions that are visited. So we will have a modified master equation with a simple random walk term here and a memory term. And the memory term, well, we can convince yourself that it takes a very simple expression, which is here. So the process is a bit equivalent, or it's completely equivalent, to choose a time t prime in the past, uniformly between 0 and t, and to reset to a position that you was occupied at time t prime. So, and if that position t prime is equals to n, so that gives a probability to revisit a particular site n. So the idea is that if you choose a time t prime completely uniformly in the past, you will have 5 opportunities to pick the site n. Then it will be the probability to revisit n will be proportional to the number of visits of n. So what we have here, so if you want to write a little bit more carefully, you say that you are in position n prime time t. So you have a joint probability. So you are at n prime time t, and you were at the time t prime, you were located at the site n, right? So you have a joint two-time probability, and you sum over all the possible positions where you can be at time t, and this is a two-time distribution function, and you sum it over it. So this is a marginal, and this is only a one-time distribution function, which is the same as this one. This is the same object. So this is a closed master equation. I mean, it only involves one distribution function. So it's not local in time, but you can still have an equation and solve it by some method or some other. So the main results are first that this process produces very, very small, very slow diffusion, very anomalous diffusion, because if you calculate the mean square displacement, you find that it does not grow linearly with time, but it grows linear with proportional to the logarithm of time. So it's extremely slow diffusion. But this very slow diffusion is asymptotically converged to a Gaussian distribution. So it's very anomalous in the sense that M2 is not a linear function of time, but approximately a very large time where there are some corrections that can be important, but the system very slowly converges to a Gaussian like the normal diffusion. So we have an anomalous yet Gaussian diffusion. And it is always time dependent. So there are other class of anomalies. There is a whole class or zoology of anomalous diffusion process. There are processes that are actually with a linear M2, but we do not have a Gaussian form. Here we have a Gaussian form, but we don't have the linearity. And it is always time dependent. So it is different from the problem of events and margin large. So if we apply this model to real data, actually we find that they can describe quite quantitatively some movement of capuchin monkeys in a place in Panama, in the Colorado island. So this is a 1 month trajectory of a monkey in the wild in its habitat. And there are several quantities that can be calculated by doing simulation, because some of them are really tough to obtain analytically, like from, for instance, time average mean square displacement, or the number of distinct visited sites by the walker on the discrete space. And we find quite good agreement, provided that this parameter Q, which is a memory parameter, is chosen different from 0. So if it's taken equals to 0, here we would have a straight line going very fast to a very high value, and the memory very quickly produce a very slow growth, nearly saturation, a slow growth of the mean square displacement. And another consequence of the preferential rule is that many places are visited, very few places are visited very often, and many places are not very much visited. So we have basically a power law distribution for the distribution of that quantity mi, which is the number of visits received by a site I, picked at random. And so the model predicts that. The data also shows exhibit that. With a similar exponent. So, this model is simple. It can capture some non-anomalous aspect of diffusion in a living organism. So now we wanted to extend this process to generalize this reinforced process to continuous time process. For instance, assume that you have arbitrary Markov process. So it can be Brownian motion or anything, basically. And you use this preferential resetting with memory. So during a time interval, very small time interval, with the probability R times dt, you reset to a previous position. And so you choose a time uniformly in the interval 0, and you, for instance, use time, and you reset to the position that was occupied at that time. So you restart from there and you continue your Markov process. But then you repeat many times. And and with the complementary probability, you don't do anything, you just continue your Markov process. So one question is how the memory process is related to that underlying process. We can, if we know everything about that process, without any resetting, R equals to 0, what can we say about the process when R is going to be different from 0? So again, revisit to familiar places principle. So let us consider an underlying process with given by a propagator or by occupation probability. So that's the probability to be around the position x at time t. So the zero means that we don't have any recipe. And this is a very general form to write a classical Markov process. So phi of L is some kind of eigenmode, and lambda L is the eigenvalue associated to that mode. So the modes relax exponentially. And this amplitude is given, for instance, by the initial condition, by the initial position. So let's assume that we have that, and that is described many different processes. So if we switch on memory, different from zero, what we can find is that the new occupation probability will be given by basically the same sum, but instead of having an exponential here, we have a more complicated function. But the phi L and the lambda L that are here for the Bayer underlying the Bayer process are the same that we find here. And the resetting rate is found here, and the function M is more complicated. There's a confluent geometric function. So which basically has a three argument and can be written this way. So the important thing here, more than these details, is that at large arguments, z, negative argument, here at large time, this decays as a power law. This is no longer exponential, this is a power. So which means that the mode n, instead of decaying exponentially to zero, it will decay to zero much more slowly with an exponent theta L that is given by this analytical value, this exact value. So typically, for instance, when you study the diffusion of particle in a bounded domain, so you see that the profile tends to a uniform distribution, right? If there is no just a free diffusion in a limited region of space, and all the modes decay exponentially. So here they will decay as a power law because of memory. So we can apply this to different setup or processes like Brownian motion in a potential, active motion, study eventually large deviation, random walks on network, any stochastic process basically, or even lady flights, which are still Markov process, and to see what is the impact of memory. So, for instance, if we start with, for instance, the Brownian particle confined in the potential. So this is a Fokker-Planck equation. So when these two terms are not present, which are the memory term, so which is a well-known, well-studied equation. For instance, if U is a harmonic potential that confines the particle, so we will have a Roche-Ulenbeck process. So the position of the particle will fluctuate between, will be Gaussianly distributed and will be fluctuate over time. And here we have some memory terms. So here we have similar to the Evans-Majumdar resetting problem. So we have a loss of probability because from any position we can leave that position and reset to somewhere else. And a gain of probability at the position x because that position was visited in the past. Right, so that's a preferential return to the position x. So if there is no potential, so this is similar to the previous case, so the simple basic model, the first example. We just have the diffusion equation, and with r equals to 0, so the elementary solution of the diffusion equation are just Fourier modes that decay exponentially with these eigenvalues, this rate lambda k, where k is a number, a real number. So if we apply the formula for this exponent that I've shown in the previous slide, which were this, so this lambda k here is known. So we have a theta k for the mode k, the Fourier mode k, which is given by this. So the amplitude of mode k is a power law. Power law is an exponential of a logarithm. So if we have this sum, which is continuous here for the probability density, so we just sum the same function phi and the asymptotic form of this function n, right? As ik is given by the initial condition. So at large t, this will be dominated by the small theta k. So when small theta k means a small k, so we can neglect this. And we see that we have the inverse Fourier transform of a Gaussian, and we know that the Fourier transform of a Gaussian is a Gaussian, so that function will tend to a Gaussian. And the mean square displacement will be given simply by 2t over r times this factor, which is low. So that's another way to recover the fact that the diffusion is extremely slow, becomes Gaussian, but is extremely slow at large time. Now, what if we have a confining potential? So let's assume that we have a Brownian particle obeying, for instance, a Langevin equation in an external harmonic potential. So this is a very common, actually, apart from the many physical application of that model, of course, it is also widely known in movement ecology to describe the fact that animals do not go away. They are kind of confined to some very to some home range. They don't. They the place where they live, basically, and this can be very simply modeled in a phenomenological way by a confining potential. That's it. I mean, there is no difference with a physical Brownian particle. So. So what is well known here is that the density, so the evolution of probability density for the position of the particle can be decomposed by a stationary part and a transient part, and the stationary part is given by the Boltzmann-Gibbs distribution, the equilibrium, and the transient part, so is basically a sum of eigenvalues. So there is a leading term, which is the smallest lambda of the problem will lead the relaxation, the exponential relaxation toward equilibrium. So a way to solve this problem is in general to make a change of variable for the probability for this mode. I mean, we make a separation of variable, and the spatial part of the solution is written by like this in a variable change, where that, and we find that psi of n is actually a solution of the Schrödinger equation with a modified quantum potential, which is a transformation of the initial potential u, and where h bar is equal to 1 and m, the mass of the particle, is equal to 2. So it's like we transform the Fokker-Plan equation to a Schrödinger equation with which is the Schrödinger of a particle of mass 1 with h bar equals to 1 in that notation. That's the equation for that psi. And so this is much easier to calculate. I mean, we can calculate analytically or numerically, depending on the complexity of the potential. And what is that? What this gives the eigenstates, the eigenvalues. So lambda equals to 0 corresponds to the ground state. Lambda 1 typically, so if the spectrum is discrete, will be the eigenvalue that dominates the large time evolution of the relaxation toward equilibrium. So now if that was for r equals to 0, which is very standard, very well known. So if r is different from 0, now we have a spectrum of exponents. So we still have theta 0 equals 0. So we have the same Boltzmann, the same decomposition, and P naught is unchanged. It's still the Boltzmann-Gibbs distribution with the final state. But now the transient part, instead of decaying exponentially, is decaying as t to the minus theta 1 at large time, because if we have a discrete spectrum, at very large time, this will completely dominate. I mean, there will be a mixture of power law behavior, but this one will be well separated from the others, and there will be one single power law which will dominate the whole dynamics. So we can call, in a way, this state as critical because there is no characteristic time scale. So the relaxation time per se is infinite. We have a scale-free relaxation toward equilibrium given by this exponent that depends on the eigenvalue of the memoryless process, the process without memory. So for the harmonic potential, lambda 1 is very easy to calculate and is given by nu, so that's equally spaced harmonic oscillator levels. And theta 1 is given by that value. And so the exponent is non-universal. It will depend on the choice of R, the resetting rate, and mu, the external potential stiffness. So for instance, another example is a Brownian particle in a box with reflective boundaries. So that's one of the examples I mentioned earlier. So here, by solving the elementary diffusion equation, this is basically the Sensia-Tuda exercise, we can find that there are eigenmodes that are discrete and discrete, are cosine function, and the associated eigenvalues are given by this expression where n is 0, 1, 2, etc. So the leading theta is when n equals to 1 and is given by this. So if we choose R to be twice this number, for instance, the exponent of the relaxation will be equal to 1/3, or if it is 3 times, it will be 1/4, etc. So we have kind of a non-universal relaxation, non-universal exponent, but scale-free relaxation, which in a way, we call it somehow self-organized criticality, in the sense that this is the own interaction of the worker with his trajectory and with the boundary of the system, or more generally with the confinement potential, that creates a very slow relaxation without any time scale in the system. This is quite general. So there is a third case, for instance, where we can have a mixed discrete and continuous spectrum. So instead of, so we still have the lambda naught, the ground state, the gap to the first excited state, and then a continuum of states. And so the situation here is basically the same, except that we have logarithmic corrections whose exponent will depend on the density of states near lambda. And that situation, which looks a little bit theoretical, actually is exactly what happens for the piecewise linear potential, so the confinement potential with a force, with a constant force, and where theta 1 is given by this. And then, so again, we see that instead of having a pure power law with t to the -1/2 in this case, for this choice of the parameter, there are some slight deviations in the numeric simulation due to this logarithmic. Okay, so maybe I will skip large deviations. Okay, maybe I will return to this, but okay. So this is, so far it's a little bit like the physical point of view of this process, but there is also a mathematical point of view of this process, which is due to these papers, and these are real mathematical papers with theorems and very long papers. I mean, minimum 50 pages. So, which kind of we take this problem and present it in another way by doing an analogy with recursive. So if we summarize the type of problems that we are dealing here, so we have a Markov process which evolves over time, then there is a reset process. So I choose a time in the past, for instance this one, and I start again from here, then there is an evolution, then I choose another time in the past, for instance this one, and I restart, no sorry, yeah, this one, then I restart from here, and so forth, right? So we have a series of runs that are separated by resetting them. And the runs are completely Markov process. So for instance, the last run up to time t shows a time in the past which was here. It belonged to a previous run, which was a run number 4, right? It started from the position occupied by run number 4. Right? And run number 4, no, 3, sorry, it was 3. And run number 3 connected to run number 1. So each time there is a resetting event, it's like creating a node for a small part of the trajectory, which connect to a previous part of the trajectory or previous node. So, and this, well, mathematically, this is a tree. So you add nodes, you start with from a root node, and you add the node one after the other, and you choose a node which is already there, and you connect to it. You choose it randomly. So here, and you obtain this kind of structures. So uh, here, so if we want to know the position at time t, we go, so we go through run 1 until this time, then we glue it with the run number 3, and the run number 3, we glue it with 7. So we have a completely Markov process from beginning to the end, right? Because we are just gluing Markov process, and they are still Markov process. So that becomes very simple in a way, because that's basically, we know exactly the distribution of the position. The problem is that this time, capital T, is much shorter than the real time T. And it's a random variable. And so the whole difficulty is taking the average over this random variable, over all the tree histories, over all the resetting, all the weight, because it's a weighted, because each node has a weight which is proportional to its length. So since it's stochastic resetting, so these run have different duration, they are exponentially distributed. So that's why they are called random weighted recursive tree, actually. So after many pages of proof, so it's possible to prove a rigorous central limit theorem, and so the limit theorem that tells us that actually this process is going to be Gaussian asymptotically. I mean, if the Markov process, or it can be a Levy flat, so it can become Levy, so if it's a Levy flat. But if the Markov process has a limiting distribution, then this resetting process will have also the same limiting distribution, but with different scaling for the time. So there is a very simple qualitative argument. So we know that in a random recursive tree, so it's like a branching process. Basically, so we can define the weight of the trees, and we know that basically the number of nodes in a tree of 8h goes exponentially with h, because it's just replicating a process. So capital T is actually proportional of the order of h, the size of the trees. So this shortcut from 0 to the current time. And T itself, the real time, is the number of nodes, right? Because nodes have finite durations, so the total number of nodes will be more or less Q times T, where Q is the visiting probability. So since h is a log of n, because it's a tree, so we deduce that capital T is roughly the log of t. So we recover this log t scaling that we observed since the beginning. And this can be generalized to any other Markov process, even for any distribution of resetting, so not necessarily exponentials, and can be extended also when memory is decaying. For instance, when memory is decaying, you remember more the recent nodes, so you have a higher probability to connect to the last nodes and not that much to the first nodes, and that modifies the weight, and that can modify the distance scaling. And, okay. So just to finish, I would like to show how a very tiny modification of the model rules can lead to completely different results. These different results are basically localization phenomena. localization phase transition. So let us assume a very simple generalization of the model that we have a state-dependent resetting probability. So we have the same model as before. So the random walk is hopping on the side, nearest neighbor, and with some probability can come back to a previously visited node, right? With a probability Q. But when it is on the origin, or some site, or wherever, it does not reset. It stays, so it does automatically a random step, so either to this guy or to this guy. So there is no reset from the origin. You cannot go there, from there to there. So that means that you stay a little bit longer at the origin than on the other side, or the vicinity of the origin. So this is a very simple way, so there are several variants that can be studied to introduce the fact that the worker is working in a heterogeneous environment where there are food, for example, resource patch. So he will not leave that easily a resource patch than any other empty patch, right? So he's walking around, resetting, searching, and when he's there, he's just kind of stay a little bit longer, so this site will be reinforced. So if you remember, there was this memory parameter in the master equation that just depends on the sum of the previous time, the distribution as the previous time. So more generally, it is given by this. So you are at a given site n prime time t, and you want to go to n that was visited in the past because you want to visit this site because it is preferential, right? And so if Q of depends on the position, we cannot take it out of the sum, and we cannot take the marginal of this distribution. So we cannot get rid of that function. So the problem, when you write the master equation for the single time distribution, we have there is this term which appears, which is a two-time distribution function. So which means that you need to now to have a second equation for the two-time distribution function. Will appear to depend also on the three-time distribution function. So there is a whole hierarchy of there is not one equation, there are an infinite number of equations. So the problem is not closed, and it is fully nonlinear because this object is very different from P of n, just so. And this gives rise to completely different property. And one is if we approximate, this function as a product of the 2p of single time, the decoupling approximation, that we think is actually exact at the infinite limit, we obtain, instead of having a Gaussian distribution that diffuse slowly over time as a log, we have an S non-equilibrium steady state. So you have a non-trivial finite asymptotic distribution, which is roughly exponential, at least at the time, and which is characterized by a correlation length, which tells where is localized, where the worker is localized near the origin. And what we find is so P naught, which is different from zero because there is stationary state, satisfied. So there is a trivial solution, which is P naught equals to zero. Of course, if we put P equals to zero everywhere, so it's a trivial solution of the equation. There is no worker. The no zero worker case is the solution, trivial solution of the problem. But there is also another solution which is not trivial, which is this one. And that satisfies a transcendental equation, which is given by this. So here for the nearest neighbor, this P of k, half of k would be a cosine of k. Simply. So that's the transform. And okay, so this is not that, so this can be solved numerically, and we find typically that there is a transition, a phase transition between the localized phase and the non-localized phase, where P not equals to zero is the only solution, acceptable solution. So And this depends on the memory parameter Q. So if I use memory often, I will localize around that size, but below a critical value of the memory parameter or the resetting probability, the worker will diffuse away to infinity and will not occupy that size. Although it will diffuse very, very soon. And this QC, that particular problem is kind of funny, so that's why I put back the photo of Polya. That critical resetting probability is exactly given by the no-return probability. So the no-return probability is a probability that is a very well-known old result. Is a probability that simple random walk on a lattice never returns to the origin, to the starting position. So in 1D and in 2D, it is zero, because random walker always come back when they take a long time to do so, come back to their starting position. So which means that in 1D and 2D, so this example is a 2D lattice, for instance, we always have the non-trivial solution because QC will be zero. So for any small amount of memory, the walker will become localized for a simple random walk. But for instance, if we imagine a 3D lattice, then there will be a phase transition because P no return probability for a cubic lattice, for instance, is 0.34, something like this. And so that there will be, so there is a competition between the recurrence property of the simple random walk, very well known phenomenon, and the resetting probability. So when the resetting probability is bigger than the probability to escape, then memory wins and there is a localized state. And actually, quite strangely, these equations are very similar to these, are also well known in condensed matter for some approximation of the localization of the Anderson transition. Actually, this belongs to the self-consistent, this is similar or equivalent to the self-consistent theory for Anderson localization. And of course, the quantities are very different, meaning and physical origin, but there are some critical exponents that one can derive for this how this order parameter goes from zero, or how the localization lengths diverge. So the critical exponents are the same as the one of the self-consistent theory of Anderson localization. So, and here, this is actually, we think that it is an exact result because it only depends on the decoupling approximation, but we are not able to show that it is actually exact. Okay, so that this is an example of simulation showing the phenomenon with a Levy flight. So Levy flights in 1D, they are not recurrent. So you can study a 1D, so you can have this phase transition, which is not possible for a simple random walker in 1D. You can have it with a Levy flight with a critical parameter too. So that's basically it. So I would like to conclude that, recall that. So we have these models of path-dependent random walk, which are exactly solvable. They can be applied to animals and maybe humans, although we have mainly animal data. And that allow us theoretically to study the effect of strongly non-Markov effects on diffusion, and which is quite flexible because we can adapt it to a free Brownian particle to particles in potential. I have not talked about the random walk-on networks, but it is exactly the same phenomenology. There can be extensions to memory decay, to a problem that Shoam and others who are studying, which are interacting random walk with memory. They can use their memory and the memory of others, so they're interacting. And therefore, in a way, it's transferring information, giving rise to collective learning. So in the previous slide, I identified the localized phase with learning, because you learn that there is a food and you stay there, or not learning, so you're not able to fix so there is a problem of first passage, which is a very challenging problem, which is completely open because it's a very complicated problem, similar to this. So which arises from this. But here, at least we could do the t goes to infinity, which simplifies everything because there's nothing dependent on time, right? But in the first passage, we have to deal with a full temporal solution. So that's something really quite horrible to do in principle. So, and we would like to thank collaborators, which are theoretical physicists, and some of them also are biologists, like Gabriel and Meg, that study primates and students mostly at UNAM. And so thank you very much for your attention.
Questions?
I have a question to this localization slide. So you just said that you relate learning with the case where Walker stays close to scientists. But this is the memoryless case, right? This is the case where he really does not use the memory.
Yes, it does. Yeah, because on all these axes you use memory. I mean, is Q is different from 0. Q is a memory parameter. So as soon as it is non-zero, you use memory. So, but it tests so that memory might be enough. I mean, that use of memory might be enough or not for learning.
It depends the complementary. You make the complementary decision, right? You just do not go to the sites you have visited before.
Yeah, I mean, so you in the model as it is now, I mean, yeah, you have a mixture of two modes, right? Purely random, which complementary probability with complementary probability happens with probability 1 minus q. So this is a random step. So you needed to explore space, right? I mean, there is a random exploration of space. You visit this place a certain number of times just by chance, and then you decide to return to this place by the memory parameter q. So you fly over the lattice and directly you get to this particular. So everything, when q is different from 0, you have memory. If it is 0, it's a simple random walk. And for q equals 0, actually p naught is always 0 in all the cases. Now you can think about you can think about other generalization where you would not go to a site that you would like to avoid the site that you have been before. It's a completely different class of problems.
So there is a probability you go back to the 0 step and you reset.
Yes. Yeah, so there is a probability you can go from there to there, but you cannot go from there to the others. But you can, of course, come back to that side. It's part of the reinforcement, of course. But but all the sites are equally, I mean, follow the same. You go to that site, but you can also go to any other site. Just it happens that that site is a little bit more likely, or the neighboring ones, which is in this region, meta site will be much more likely than the others. But it is, let's say, an emergent phenomena in the sense that the worker does not know that here there is something special. It's just this work is going there because of the rule of going back to places, whatever they are, where they are often. So it's a kind of modification of the behavior that due to the experience, so that's what we call learning. Yes.
In the this square well case, um, I didn't. I think you showed that the variance increases, right, with all limits.
Even this one?
The square well, yeah, in this particular course.
Yeah.
But it should.
No.
Oh no, it decreases.
No, I mean, yeah, sorry, I was kind of fast here. So this is the mean square displacement. The square displacement, square position. And there's minus the asymptotic value, which is finite. So that guy tends to a constant, which is, I think, L over 3 or something like that. L square over 3. So yeah, it tends to the uniform distribution. So the thing is that it's still equilibrium process. Actually, it is possible to show even that detailed balance is satisfied. So it's at long time. So it's like an equilibrium process, despite of the memory. It tends towards a completely uniform distribution. So as because the potential is 0 everywhere in the interval, so the equiprobability of occupation. But the relaxation, so that's the leading mode, relax as a forward, not exponential. In the typical exercise on diffusion. And the same thing happens on networks. So on networks, there's the same problem. Locally, the probability distribution tends toward at a node, tends towards the limiting distribution. But there is a correction, which is a power law that decreases slowly. And it depends on the smallest eigenvector, non-zero eigenvalues of the network. So any discrete problems or finite problem, finite Markov problem, will lead essentially to this kind of power decay. That's it. The equivalent of the exponential here would be a power.
So hay alguna relación
Pues, in this one particular, no. I mean, yeah, it could be in a way we didn't with the monkeys. It's an open, it's a free diffusing particle. So there is no boundary, no potential, and that's enough to capture the data. So that was the first version of the model. Is that version of the model. So there is no wall, no external potential. Of course, it is very idealistic because, for instance, there is obviously some limit to the island. So, but as we see, that I mean, there are maybe some other force that act on the monkey, which is not memory. For instance, other monkeys with whom they fight, so they want to avoid them and stuff like that. So yeah, probably that would be more realistic to assume that actually there is a confining environment here that we don't know exactly what it is. But yeah, for sure. But as a first step, okay, we ignore this, and that was enough because log function, the log is so slow that it's nearly a constant. So it's nearly as if you were localized. it's nearly on the time scale that we study, it's enough.
So there is no more questions, and there is thank the speaker because I